This is the video for Section 2.1, Congruence and Congruence Classes. In Chapter 1, we examine the properties of the integers in detail. In this chapter, we want to introduce a new system of numbers which share many of the same arithmetical properties as the integers. The construction of sets of congruence classes will serve as a model for many similar constructions in the rest of the course. In this first section, we introduce the concept of congruence modulo n on the set of integers. We can view this as a generalization of the equality relation. Two integers a and b are equal provided that their difference is 0, or equivalently, their difference is a multiple of 0. For any positive integer n, we say two integers a and b are congruent modulo n provided that their difference is a multiple of n. That is, a minus b is equal to kn for some integer k. Note that this condition is equivalent to saying that n divides a minus b. We then have the formal definition. Let a, b, and n be integers with n greater than 0. Then a is congruent to b modulo n, which is denoted with the notation shown. So we have a is congruent to b and then mod n in parentheses, provided that n divides a minus b. For a quick example, we can verify the following. 24 is congruent to 3 mod 7, and 15 is congruent to 64 mod 7. For a, since 24 minus 3 is equal to 21, and 7 divides the difference, 21, then 24 is congruent to 3 mod 7. For b, since 15 minus 64 equals negative 49, and 7 divides negative 49, then 15 is congruent to 64 mod 7. Now in the notation a is congruent to b mod n, note that the symbols, the triple equal sign, and the mod n are really parts of a single notation. So by itself, writing a with the triple equal sign b is meaningless. So an alternative approach to looking at congruence modulo n is to consider the remainder upon division by n. So for all integers a, b, and n with n greater than 0, a is congruent to b mod n if and only if a and b have the same remainder upon division by n. So this result will be a homework exercise. For example, suppose we want to find all integers a such that a is congruent to 3 mod 7. Now an integer a satisfies the condition a is congruent to 3 mod 7 provided that 7 divides a minus 3, which holds provided that a minus 3 is equal to 7k, or a is equal to 7k plus 3 for some integer k. It follows that the integer satisfying this condition will be, well, negative 11, negative 4, 3, 10, 17, and so on. By the above remark, these are the integers with remainder 3 when divided by 7. Now the relation of congruence modulo n shares many of the same properties as the relation of equality. For example, equality satisfies the following 3 properties. First, the reflexive property, which states for all integers a is equal to a. Second, the symmetric property, for all integers a and b, if a is equal to b, then b is equal to a. And third, the transitive property, for all integers a, b, and c, if a is equal to b and b is equal to c, then a is equal to c. The next theorem shows that congruence modulo n also satisfies these 3 properties. So this is theorem 2.1. Let n be a positive integer. And then first we have the reflexive property. For all a and z, a is congruent to a mod n. 2. The symmetric property. For all a, b, and z, if a is congruent to b mod n, then b is congruent to a mod n. And 3. The transitive property. For all a, b, and c in z, if a is congruent to b mod n, and b is congruent to c mod n, then a is congruent to c mod n. To prove this, we'll start with the reflexive property. So suppose a is an arbitrary integer. We need to show that a is congruent to a mod n. According to the definition, to show this, we need to show that n divides a minus a. Well, since a minus a is 0 and n divides 0, then this holds. So a is congruent to a mod n. For 2, the symmetric property, we'll suppose a and b are arbitrary integers. Suppose the hypothesis a is congruent to b mod n, and we need to show the conclusion b is congruent to a mod n. Now to show this conclusion, we need to show that n divides b minus a. Now from the hypothesis, since a is congruent to b mod n, then n divides a minus b. And note that b minus a is just minus the quantity a minus b. And by a lemma in section 1.2, since n divides a minus b, then n must divide minus a minus b, or b minus a, as required. And therefore b is congruent to a mod n. For 3, the transitive property, we'll suppose that a, b, and c are arbitrary integers. Suppose the hypothesis a is congruent to b mod n and b is congruent to c mod n. We need to show the conclusion a is congruent to c mod n. And to show this, we need to show that n divides the difference a minus c. From the hypotheses, since a is congruent to b mod n, then n divides a minus b. And since b is congruent to c mod n, then n divides b minus c. And note that a minus c will be equal to a minus b quantity plus b minus c quantity. And by the lemma in section 1.2, since n divides a minus b and n divides b minus c, then n must divide their sum, so therefore n divides a minus c as required. And therefore a is congruent to c mod n. And this proves 3, and this completes the proof of the theorem. Now note that equality is preserved under addition and multiplication. That is, for all integers a, b, c, and d, if a is equal to b and c is equal to d, then a plus c equals b plus d, and a times c is equal to b times d. So basically we can add 2 equations together, or we can multiply them together, and the equality is preserved. The next theorem shows that the same properties hold for congruence. So this is theorem 2.2. Let n be a positive integer. Then for all a, b, c, d, and z, if a is congruent to b mod n and c is congruent to d mod n, then first a plus c is congruent to b plus d mod n. We can add 2 congruences together. And second, a times c is equal to b times d mod n. So we can multiply congruences together. So to prove this, well, let's suppose that a, b, c, and d are arbitrary integers. We'll suppose the hypotheses a is congruent to b mod n and c is congruent to d mod n. Then n divides a minus b and n divides c minus d. And for 1, we need to show that a plus c is congruent to b plus d mod n. To show this, we need to show that n divides the difference, a plus c quantity minus b plus d quantity. Now since n divides a minus b and n divides c minus d from our hypotheses, then by that lemma in section 1.2 again, n must divide the sum, a minus b plus c minus d. And rearranging terms, this is equal to the quantity a plus c minus the quantity b plus d. And that's what we needed to show, that n divides that. And therefore a plus c is congruent to b plus d mod n. And this proves 1. Now for 2, we need to show that a times c is congruent to b times d mod n. And to show this, we need to show that n divides the difference, ac minus bd. Now note that ac minus bd is equal to ac minus bc plus bc minus bd. So what we've done is we've subtracted bc and added it back in so that we preserve the equality. Now, the first two terms have a common factor of c, which we can factor out, and the third and fourth terms have a common factor of b that we can factor out. And so we obtain this is equal to a minus b quantity times c plus b times the quantity c minus d. Now, since n divides a minus b and n divides c minus d, then by the lemma in section 1.2, n must divide this linear combination, a minus b times c plus b times the quantity c minus d. And therefore n divides ac minus bd. And hence ac is congruent to bd mod n. And this proves 2. For an example, we can use the theorem to find the remainder when 1 factorial plus 2 factorial plus 3 factorial all the way up to 99 factorial plus 100 factorial is divided by 12. Okay, well, this is obviously an enormous number, and we don't want to actually compute it all out, but we can use congruences to determine the remainder when we divide this number by 12. And first note that 1 factorial is just 1, which will be congruent to 1 mod 12. 2 factorial is 2, which is just congruent to 2 mod 12. 3 factorial is 6, which is just congruent to 6 mod 12. Now 4 factorial is 24, and that's congruent to 0 mod 12, since 12 divides into 24. Now, since 5 factorial is equal to 5 times 4 factorial, then by the second part of theorem 2.2, 5 factorial will be congruent to 5 times 0, which is congruent to 0 mod 12. So since 4 factorial is congruent to 0 mod 12, multiplying that congruence by 5 will obtain 5 factorial is congruent to 0 mod 12. And similarly, for each k equals 6, 7, all the way up to 100, since 4 factorial will be a factor of k factorial, then k factorial will be congruent to 0 mod 12. Then applying the first part of theorem 2.2, we then have 1 factorial plus 2 factorial plus 3 factorial plus 4 factorial all the way up to 100 factorial will be congruent to 1 plus 2 plus 6 plus 0, and then a string of zeros all the way up to a 0 for 100 factorial. And this is all mod 12. And so this is just 9 mod 12. Now the remainder, so then the remainder when this sum 1 factorial plus 2 factorial plus 3 factorial up to 100 factorial is divided by 12 will be 9. Next, we want to talk about equivalence relations. In general, for any set A, a subset of the Cartesian product of A cross A, so this is the set of ordered pairs AB, where A and B both come from the set A, is called a relation on A. Now, if T is a relation on A, we write A tilde B, provided that the ordered pair AB belongs to T. Now, a relation T is an equivalence relation on A, provided that it satisfies the following 3 properties. The reflexive property, which states for all elements A in A tilde A, or A is related to A, is how we can read that. 2, the symmetric property, for all AB in A, if A tilde B or A is related to B, then B tilde A, B is related to A. And 3, the transitive property, for all ABC in A, if A is related to B and B is related to C, then A is related to C. Now, theorem 2.1 shows that congruence modulo n is an equivalence relation on Z, since it satisfies these 3 properties. So for some simple examples, let A be any set, and we can define A tilde B to mean A equals B. Now, as stated earlier, equality satisfies these 3 properties, the reflexive, symmetric, and transitive properties. So this will be an equivalence relation. For another example, let's let R be the set of real numbers and define for all elements R and S in R tilde S, or R is related to S, provided that the absolute value of R equals the absolute value of S. Now it's straightforward to verify that this relation satisfies the three properties, so will be an equivalence relation. For another example, let's let R be the set of real numbers and define for all R and S in R tilde S, or R is related to S, provided that R is less than or equal to S. Then this is not an equivalence relation. So to show this, we need to show that our relation tilde does not satisfy one of the three properties. Now this relation does satisfy the reflexive and transitive properties. So for all real numbers R is less than or equal to itself. And for three real numbers, R, S, and T, if R is less than or equal to S and S is less than or equal to T, then R will be less than or equal to S. So it satisfies both of those properties, but it does not satisfy the symmetric property. And to show that it does not satisfy the symmetric property, we need to show that the condition in the property for all R and S in R is related to S implies S is related to R is false. And to show this is false, we need to find a counterexample. So let's let R be 2 and S be 3. Then R is related to S since 2 is less than or equal to 3. But S is not related to R. S is related to R does not hold since 3 is not less than or equal to 2. So our hypothesis is true, but our conclusion is false, which makes this conditional false. Therefore, the symmetric property does not hold, so this relation is not an equivalence relation. Next, we want to talk about equivalence classes. So let's suppose that tilde is an equivalence relation on a set A. For each element A in A, the equivalence class of A, which is denoted by A in square brackets, is the set of all elements in A that are equivalent to A. So that is, the class of A is the set of all B in A such that B is related to A. For example, we can find the equivalence classes for the equality relation on the set Z of integers. So, according to the definition, for any integer A, the class of A will be the set of B in Z such that B is related to A, which in this case means B is equal to A. And so this will just be the set containing A itself. So each equivalence class consists of a single element, or a set containing a single element. For another example, let's find the equivalence classes for the equivalence relation on R. R is related to S provided the absolute value of R is equal to the absolute value of S. So according to the definition, for any real number R, the class of R will be the set of S in R such that the absolute value of S equals the absolute value of R. And so this will just be R and minus R. Those will be the two real numbers that have the same absolute value as R. For instance, the class of 1 will be the set containing 1 and negative 1. And note this will also equal the class of negative 1. So each equivalence class consists of two elements, except for the class of 0, which will contain only 0, a single element. Now the following theorem and corollary appear in Appendix D of the text, but we want to cover them in this section. So this is theorem D.1. Let tilde be an equivalence relation on a set A. Then for all A, B, and A is related to B if and only if the class of A equals the class of B. So this result is saying that two elements are related according to the equivalence relation if and only if their classes are equal to one another. So for the proof, we'll suppose A and B are arbitrary elements of A. Now the theorem contains a biconditional statement, so we need to prove the forward direction, which states A is related to B implies the class of A equals the class of B, and the backward direction, which says that the class of A equals the class of B implies that A is related to B. So for the forward direction, we'll suppose A is related to B, and we need to show that the class of A equals the class of B. Now note that the class of A and the class of B are both sets. And to show that two sets are equal, we need to show that they contain precisely the same elements. So the standard approach is to show that each is a subset of the other. So that's what we'll do here. So to show that the class of A is a subset of the class of B, we need to show for all C in A, C is an element of the class of A implies that C is an element of the class of B. So to prove this, we'll suppose C is an arbitrary element of A. We'll suppose that C is in the class of A. We then need to show that C is in the class of B. Now since C is in the class of A, then by definition C is related to A, or C tilde A. Since C is related to A, and by our original hypothesis A is related to B, then by the transitive property C is related to B. So C tilde A and A tilde B implies C tilde B. And this implies that C is an element of the class of B. So we've shown that every element in the class of A is also an element in the class of B, and therefore the class of A is a subset of the class of B. Now to show the opposite inclusion, the class of B is a subset of the class of A, we need to show for all D in A, D is in the class of B implies D is in the class of A. So we'll suppose that D is an arbitrary element of A. We'll suppose D is in the class of B, and we need to show that D is in the class of A. And since D is in the class of B, then D is related to B. And by our original hypothesis, A is related to B, which by the symmetric property implies B is related to A. Then, since D is related to B and B is related to A, by the transitive property, D is related to A. And this implies that D is in the class of A. So we've now shown that every element in the class of B also belongs to the class of A, and therefore the class of B is a subset of the class of A. And since we've now shown that the class of A is a subset of the class of B, and the class of B is a subset of the class of A, then the two classes must be equal to each other. And this proves the forward direction. Now for the backward direction, we'll suppose that the class of A equals the class of B, and we need to show that A is related to B. Note that since A is related to A by the reflexive property, then A belongs to the class of A. Since A is in the class of A, and the class of A is equal to the class of B, that tells us that A belongs to the class of B. And this implies that A is related to B as required. So this proves the backward direction, which completes the proof of the theorem. Okay, next we want to look at corollary D.2. And this says, let tilde be an equivalence relation on a set A, then any two equivalence classes are either identical or disjoint. So for the proof of this, let's suppose that class of A and class of B are arbitrary equivalence classes. We need to show that the two classes are either identical or disjoint. So we'll suppose that they're not disjoint. We then want to show that they must be identical. That is, that the class of A equals the class of B. Now by the theorem, to show that the two classes are equal to one another, we can show that A is related to B. Since the class of A and the class of B are not disjoint, then there exists an element C in their intersection. Since C is in the class of A, then C is related to A, And by the symmetric property, this implies that A is related to C. Since C is in the class of B, then C is related to B. Then A is related to C and C is related to B imply, by the transitive property, that A is related to B. And that's what we needed to show. And therefore the class of A equals the class of B. And this proves the corollary. Now, a partition of a set A is a collection of non-empty, pairwise disjoint subsets of A whose union equals A. So let's suppose that tilde is an equivalence relation on a set A. Then for any element A in A belongs to the class of A by the reflexive property. This means that the union of all the equivalence classes equals A. By the corollary, distinct equivalence classes are pairwise disjoint. They have no elements in common. And so this proves the following result, which we'll state as a remark. For any set A with an equivalence relation, the distinct equivalence classes of the equivalence relation form a partition of the set A. Next, we want to look at congruence classes. So our definition is, let A and N be integers with n greater than 0. Then the congruence class of A modulo n, which it will denote with the square bracket notation, is the set of all integers that are congruent to A modulo n. Or in symbolic form, the class of A is equal to the set of B and Z, such that B is congruent to A mod n. So therefore, the congruence class of A modulo n is just the equivalence class of A under the relation of congruence modulo n. For example, we can find the congruence class of 3 modulo 7. So according to the definition, the congruence class of 3 modulo 7 will be the set of A and Z such that A is congruent to 3 mod 7. And the integers which are congruent to 3 modulo 7 will be the integers which have a remainder of 3 when divided by 7. So the class of 3 will be the set ... minus 11, minus 4, 3, 10, 17, 24, and so on. For another example, let's find the congruence classes of 0, 1, 2, 3, and 4 modulo 5. So the class of 0 will contain the integers which have a remainder of 0 when divided by 5. So this will be all the multiples of 5. The class 1 will contain the integers which have a remainder of 1 when divided by 5. So the other classes can be similarly described. So the class of 0 will contain minus 15, minus 10, minus 5, 0, 5, 10, 15, 20, and so on. So these are all the multiples of 5. The class of 1 will contain negative 14, negative 9, negative 4, 1, 6, 11, 16, 21, and so on. So these are all the integers that have a remainder of 1 when divided by 5. The class of 2 will be the set containing negative 13, negative 8, negative 3, 2, 7, 12, 17, 22, and so on. And the class of 3 is as shown, and the class of 4 is as shown. And we're missing a brace on the right side of the class of 4. Since congruence classes are the equivalence classes for the congruence relation, then theorem D.1 and corollary D.2 will apply for this relation. So the following theorem and corollary are restatements of the theorem and corollary. So theorem 2.3 is a restatement of theorem D.1, and this says for all A, B, and Z, A is congruent to B mod n if and only if the class of A is equal to the class of B. So theorem D.1 said two elements are related according to the equivalence relation if and only if their equivalence classes are equal. And so that's what this theorem 2.3 says for the congruence relation. Two integers are congruent mod n if and only if their congruence classes are equal. And then corollary 2.4 will be a restatement of corollary D.2. And this says that two congruence classes modulo n are either identical or disjoint. Now the following corollary contains some additional results about congruence classes. So this is corollary 2.5. Let n greater than 1 be an integer, and let's consider congruence modulo n. And then first, for any integer a, if r is the remainder when a is divided by n, then the class of a is equal to the class of r. And 2, there are exactly n distinct congruence classes, namely the class of 0, the class of 1, the class of 2, all the way up to the class of n minus 1. To prove this, for 1, we'll suppose a is an arbitrary integer. We'll suppose the hypothesis r is the remainder when a is divided by n. We then need to show that the class of a is equal to the class of r. Now, since r is the remainder when a is divided by n, then the division algorithm implies that there exists an integer q such that a is equal to qn plus r, and 0 is less than or equal to r is strictly less than n. So then a minus r equals qn, which implies that n divides a minus r, and this implies that a is congruent to r mod n. It then follows from theorem 2.3 that the class of a is equal to the class of r. So if two integers are congruent to one another mod n, then their congruence classes are equal. So this proves 1. For 2, we need to show there are exactly n distinct congruence classes. So let's suppose that a is an arbitrary congruence class. Suppose r is the remainder when a is divided by n. Then r is one of 0, 1, 2, up to n minus 1. Those are the possible remainders when a is divided by n. So by part 1, the class of a is equal to 1 of the class of 0, the class of 1, the class of 2, all the way up to the class of n minus 1. And this shows that these are the only possible congruence classes. We still need to show, however, that these are all distinct. To show this, we'll use a proof by contradiction. So let's suppose that 2 of these classes, the class of 0, class of 1, class of 2, up to the class of n minus 1, are equal. Say the class of t is equal to the class of s for some s and t, with s and t between 0 and n minus 1, and s is strictly less than t. So 0 is less than or equal to s, is strictly less than t, is less than or equal to n minus 1. We then need to derive a contradiction. Now, since the class of t is equal to the class of s, then theorem 2.3 implies that t is congruent to s mod n. And hence n divides the difference t minus s. However, t minus s must be strictly greater than 0 and less than n, so n cannot divide t minus s. And this is a contradiction. And thus our congruence classes 0, 1, 2, up to n minus 1 are all distinct. And so this completes the proof of 2. We're going to denote the set of all congruence classes modulo n by z sub n. And so the preceding corollary implies that z sub n has exactly n elements. For example, the set Z5 consists of the 5 congruence classes, the class of 0, class of 1, class of 2, class of 3, and the class of 4. Now note that the elements of Z5 are sets of numbers. Also, each congruence class can be represented in many different ways, in fact in infinitely many ways. For instance, the class of 2, which contains -8, -3, 2, 7, 12, 17, and so on, can be written as the class of -3, or the class of 7, or the class of 32. So in fact, any element which belongs to the congruence class can be used as the class representative. And this completes our lecture.